Now we have the Cayley Hamilton theorem, which says basically that an operator t satisfies its own characteristic polynomial. So in other words, well, this looks like we're saying t is the zero of a polynomial, but keep in mind right here, this is an operator. So we're actually saying that chi of t is the zero operator, right? Okay. Now, to prove it, it's actually not too difficult with the machinery that we've already developed. So just to fix the notation, suppose we've got our characteristic function, or characteristic polynomial of t as z minus lambda 1 d1 multiplied through z minus lambda m dm. So that's the notation for our eigenvalues and their multiplicities. And so this is going to be the characteristic polynomial of t with distinct eigenvalues lambda 1 through lambda m and corresponding multiplicities d1 through dm. Okay, so now for each k, if we just look at the restriction of t minus lambda k to the corresponding eigenspace, we know that t minus lambda ki, if we restrict it to the kth generalized eigenspace, that guy's going to be nilpotent. And we know that the dimension of g lambda k is a big enough exponent to raise this nilpotent operator to kill it. So if we take this guy and we raise it to its dimension, which is dk by definition, this is going to be equal to 0 by 818. So 818, that was the one that says that n raised to the dimension v power is the 0 operator. Okay, so now, since v is the direct sum of all of these generalized eigenspaces, then we can construct these operators on each of those g lambda k's and then string them back together. So in other words, we can write a general element in v in terms of this decomposition in generalized eigenspaces. So we'll have u1 up through um with with uk in g lambda k. And then if we look at what the operator chi tt does to this v, well, we can first off by linearity distribute it. And then I can rewrite. So let's see. So my operator chi t looks like the product of t minus lambda ki to the dk, k equals 1 to m. So it's just a bunch of these factors, right? Now what I'm going to do is I'm going to pull out the first factor in the first term. So we'll have here, this is going to be the product of now all except for the j equals 1, and we have t minus lambda j I to the dj, and then I'll put the lambda 1 term here right next to u1. And now I can do that because I can reorder the terms that appear here by 520b, which says that if you have polynomials in T, they commute with each other. And that's exactly what we have here, is polynomials in T. And so then the next one, I'm going to do like the same kind of thing. I'm just going to pull out the second term. So here's all the ones where j is not equal to 2. And then I put the one at the end here where j is equal to 2. So it's next to u2. Oh, and that's d2. I forgot also the power on that first one. There we go. Power's now back. And so here's the one where I've got all terms except for the last one. And then I've got the last one. Whoops, that's the nth. Mth, raised to the d, m. And that's m. Sorry, I had to fix some m's there. Okay, and this is up against um. Okay, and then looking at these, here we've got u1 is in the lambda 1th eigenspace, so this here is going to get killed. And u2 is in the lambda 2th generalized eigenspace, so this is going to get killed, and so on and so forth. So we end up with zeros. The end. So that shows you that chi t of t is the zero operator.